Video number 2, all about limiting reactants and reagents. Why are they called reactants and reagents? It's two different words that mean the same thing. I will call it limiting reactant most often. Your book actually refers to it as a limiting reagent somewhat frequently. It's the same thing. Limiting reactant is a reaction that's used up first. If we have the reaction 2NO plus O2 becoming 2NO2, if pictorially it's represented this way, how can I determine who is the limiting reactant? Well, I could count my atoms for one, or I can look at my products for another. So in the end, in the products, I see that I've got 1, 2, 3 molecules that are not NO2. 3 O2 molecules are in there. Those are leftovers. NO must be the limiting reagent because O2 is excess. I've got 3 little extra O2s down here saying that did not get completely consumed. That's extra, so all of the NO must have been consumed. So we will sometimes answer questions about who is the limiting reactant. We will sometimes answer questions about which reactant is in excess. We'll sometimes answer questions about which or how much of the excess reactant is there. All kinds of questions like that. We will also answer questions like, what is the percent yield of this reaction? What? Let's define percent yield first. Because of the way chemical industry works, if you talk about this reactor vessel, it could maybe hold 500 tons of material, and that one can hold 5 tons of material. You're obviously going to get different things, different amounts of product out in the end. So instead of comparing actual numerical values, you compare percentage values. Percent yield is a super common way to talk about our reactions and how much product we get out of it in the end. This is the actual formula for percent yield. This is not a formula I will provide you. There will be some equations and things that I will provide you. Percent yield is not one of them. Percent yield is actual over theoretical times 100. Okay, what is our actual yield? That's the amount that you actually obtain in the reaction. It's what we measure in the lab, or if given a wordy problem, it's what you are often given in a wordy problem. The theoretical yield is the amount of product that would result if everything went perfectly according to plan. If you had perfectly precise amounts and every single atom from the beginning, reactant atom from the beginning, becomes a product atom in the end. Perfection. The maximum amount of product that can be produced, that's something that you calculate based on reaction grams and things that you're given. 100% yield is not super likely. If you ever do a reaction in person, not very likely to give you a 100% yield. You are very likely to obtain less than you should have. Okay. So back to this problem. When starting this reaction with this many grams of S8, unlimited amount of chlorine, this much stuff is collected. What's the percent yield? Okay. S8 is a reactant. Chlorine is a reactant. S2Cl2, product. So from this, I can identify this is my starting amount of my limiting reactant. How do I know that's my limiting reactant? Because it says an unlimited amount of my second reactant, an unlimited amount of chlorine. So S8 is my limiting reactant. This 6.55 grams of product, that's one of my yield numbers. Is that actual yield or theoretical yield? Actual. It's the amount that you legitly collected. So math, let's see how to do it. We need to calculate our theoretical yield. That's if everything went perfectly and all of my S8 turned into S2Cl2. I do that as a mole conversion like we just did previously. I need to go from grams of S8 to moles of S8. S8. How many grams does S8 weigh? I calculated it to be 256.6, but I want to know moles of product, S2Cl2, moles, S8. Luckily, this is already balanced. 1 mole of S8 creates 4 moles of product, and I need to finally go to grams of product. 1 mole of S2Cl2 creates how many grams of S2Cl2? I hope you're mathing along with me. 135.04 is what I got. Do that whole string, and you get 8.55 grams S2Cl2. This is my what number? It's a yield number. It's a theoretical yield. And percent yield is actual over theoretical times 100, and we get 76.6 is what I got, percent yield. The reality is, if you get a 76.6% yield on something you do in the lab, that's not too shabby at all. As you get more experience, hopefully those numbers go up, but sometimes it's the reaction to blame, not your lab skills. That was so fun. How about some more? Urea is prepared by reacting ammonia with carbon dioxide. Water is also produced. In one process, this and this are added together. Which thing's limiting? Calculate the mass of everything formed. How much excess reagent is left at the end of the reaction? First, write a balanced equation. Well, that's ammonia and CO2 are being added together to create urea. That's supposed to be urea. NH2CO, urea, and water. This actually says ammonia and carbon dioxide. Yep. Okay. If I need to balance this thing, I've got 1 nitrogen on the left, 2 on the right. Need 2 nitrogens. I've now got 2 nitrogens on the left, 2 nitrogens on the right, 6 hydrogens on the left, 6 hydrogens on the right, 1 carbon on the left, 1 carbon on the right, 1 oxygen on the, 2 oxygens on the left, and 2 oxygens on the right. It's balanced. All I needed was a 2 in front of NH3. So if I start with 637.2 grams of this and 723.4 grams of that, which thing is limiting? We'll start with that question first. Which thing is limiting? Well, I need to go through and figure out if this is limiting, how much product could I make? Or if that is limiting, how much product could I make? So we'll go through a couple of mole calculations with those things. Anytime you're given, most of the time when you're given mass amounts for 2 reactants, it's a limiting reactant problem. You're going to have to figure out which reactant is limiting. All right, let's roll. So if all of the ammonia reacts, I started out with 637.2. 637.2 grams of ammonia. We will count hydrogen as 1.01 for this molar mass. So that makes this 17.03 grams of ammonia in 1 mole of ammonia. And then I go on to 1 mole of ammonia creates how many moles of urea? I stuck in 1 mole and 1 mole, and hopefully bells and whistles and alarms are sounding in your little brains. That doesn't match my limiting reactant. That doesn't match my balanced equation. My balanced equation says for every 1 mole of urea, you need 2 moles of ammonia to make it. So I can stop there, potentially. and calculate how many moles of urea could be created. If I do my little math, 637.2 divided by 17.03 times 2, 18.71 moles of urea could be created with 637.2 grams of ammonia. Okay. What if carbon dioxide reacted instead? What if carbon dioxide were limiting? 723.4 grams of carbon dioxide. 1 mole of carbon dioxide weighs 44. I'm carrying out all the decimals this time. 0.01. That's carbon is 12.01. Oxygen is 16.00. 44.01 grams carbon dioxide. 1 mole urea is created for every mole. This really is a 1-to-1 mole ratio, but you got to put in that bit. How many moles of carbon dioxide? No. How many moles of urea would this amount of carbon dioxide create? 16.4 moles of urea. Yep. This number is smaller than that number. Therefore, this reagent is the limiting reactant. Limiting reagent. Yep. So the way this reads up top, this says, one strategy is to calculate the maximum amount of urea that can be produced if each reactant were to react completely. The smaller amount is the theoretical yield. Well, I've stopped short of that. I only went to mole conversions, and I said my smaller number of moles is created from my limiting reactant. This blue box number is a theoretical yield number, but it's a theoretical yield of moles. It's much more common for us to talk about theoretical yield in grams. So we'll go on there now because it relates to what our next steps are. If I have 16.4 moles of urea that could be created, how many grams of urea would that make me? Urea has a mass of 60.06 according to my math. 06. So that gives me a theoretical yield of 987 grams. It's real squishy down here. Sorry. If this becomes illegible, that's not a 2. 987 grams of urea could be produced. That green number is my legit theoretical yield in grams. Much more common to talk about theoretical yield in grams. Can you talk about it in moles? Sure. Much more common to talk about it in grams. So why did we do all this? If we go back to the questions we're trying to answer, which of the two reactants is a limiting reagent? That would be CO2. Oddly enough, we had more grams of CO2, but it was consumed differently. It's consumed more slowly. What I mean by that is it has a coefficient of 1, while ammonia has a coefficient of 2. And when you do your whole mole comparison, even though the amount of CO2 is greater, that CO2 is my limiting reagent. Calculate the mass of this urea formed. We calculated it. Carbon dioxide was limiting, and we calculated that 987 grams of urea could be formed. How much excess reagent is left at the end of the reaction? We have not done that yet. Which reagent is excess? That would be ammonia. So let's do that. So how much excess ammonia? In order to know how much excess ammonia, you need to know how much you consumed from the beginning. So I can start with my point of 16.4 moles of product could have been produced because that's my moles of limiting reactant. I could also say it took 16.4 moles, or the amount of carbon dioxide that we had that was limiting was 16.4 moles. That's a good place to start to me. It doesn't mean that that's where you have to start, but it's where I'm choosing to start. Can you start all the way over with grams of CO2? Sure. 16.4 moles of urea. I want to compare to moles of ammonia because I need to figure out how much ammonia was consumed. Whew, I'm getting tired. 1 mole of ammonia. No, 1 mole of urea, 2 moles of ammonia. And we're wanting to know how much was consumed. That's implied to be a gram number, even though it doesn't specifically say. 1 mole of ammonia weighs 17.03 grams. So that tells me the amount of ammonia that I consumed was 559.8 grams of NH3 consumed. And I started with 637.2 grams of ammonia. Do a little subtraction. I have 77.4 grams of ammonia excess. I have an excess 77.4 grams of ammonia. Whew. That was a lot of work. Again, I say, limiting reactant is an important concept. Believe me when I tell you so. We'll do it again in the next video, believe it or not.